Welcome to the final exam review. I'm Jared, this is Sai and Han. We're your TAs, if you haven't known that already. Code for the review is available here. This is the GitHub page. If you don't know where this is, I would highly suggest finding it. Under STA371G, right? You go to our help, under help sessions. And we're going to be using the file final review student code. That's what you want to open up. Yes, the full code is already posted there. If you want to deceive yourself and already have the answers to the practice questions for today, you can click on that. I would highly suggest not doing that, but you are free to do so if you so choose. So if you open the student code, it will look like this. Yes, there's not much, but you don't have to type in the whole read.csv stuff. If you were here for our midterm review last time, same idea. This will have stuff so that you can fill in the gaps. And you'll get some practice, and we'll review all the concepts, okay? So without further ado, turn the time over to Sai. And the two of us not presenting will be roving, taking your individual questions. If you have a question that's applicable to the whole class, feel free to ask it. If you have like an issue or a little bug in your code, we'll help you with that individually. All right?
Alright, so there will be two parts to this review session. We'll be covering everything that's there in your syllabus. And first, we'll do a basic concepts. There'll be slides having basic concepts for all the concepts that you've studied so far. And the next part of the session will be on examples on each of those sections. So I'll start with probability here. As you know by now, marginal probabilities, joint probabilities, we've just compiled all the definitions for all these important terms in probability. What we would recommend you to do is, it would be good if you could focus on conditional probabilities, independence, and Bayes rule, because these three concepts are where there's a high probability of you getting a probability question from. So, if that's necessary, you guys focus on these three. Conditional probabilities are basically when you know one outcome, what is the probability of another outcome happening. So, probability of not B or B given A is probability of A and B by the probability of A. So, Bayes' theorem extends to the conditional probabilities where when you're given probability of A given B and you need to know the probability of B given A, you can calculate that using the Bayes rule. That's probability of A given B times probability of B by probability of A. For most parts of questions that you will be getting, this formula would be more useful than this one. Probability of B given A times probability of A by the whole probability of B is what you guys will be getting mostly. So if you can get this expanded denominator form right, then you're going to crack that Bayes theorem question. So that's about probabilities. Okay, we'll go to basic concepts in decision trees. Jared.
I don't have a lot listed here. And there's not a lot of we don't have some practice on decision trees, but not a whole lot. Reason being, we covered this very much in detail at the midterm 1 review. We've covered it in detail in a lot of classes. So here we'll review some concepts and we'll do some simple problems. And some more complex things, we'll point you to other resources. Okay? Because we'll be focusing on some of the more recent material, right? So a decision tree is a decision process. Certain parts of the decision are yours to make, or the person's to make, whoever you're modeling. Other parts are random. We call those nodes. Decision nodes versus probability nodes, or perhaps a random node, as it might be called in some texts. The whole tree happens chronologically, from left to right. You start out with some root decision, and you break down, and you create more branches as more possibilities open up, right? So that happens chronologically. Note that all probabilities are conditional on everything that's already observed. So any probability on the far right side of the tree, right, the leaves, the branches and the leaves out towards the leaves, let me rephrase that. The leaves and the branches towards the leaves are all conditional upon what happened first. much as how everything now is conditional upon what's already happened in the past. Lastly, perfect information means you have zeros and ones for your probabilities, but does not account for the actual randomness that happens. So for example, if you're going to hire an outside source and they have perfect information, the rate at which they tell you yes or no is still dependent upon whatever's going on. So if typically there's a 60-40 split between good and bad, some good and bad event in your business future, the person will tell you 60-40 correctly, but still just 60-40 whether that good or bad thing is going to happen. Important to keep in mind as you create a decision tree for perfect information. All right. Do you have any questions on decision trees in general? It's kind of in the past. Hopefully you're focused more on multiple regression, logistic regression, time series, etc.
So for Mutum 2, we cover the regression, including the simple regression and multiple regression. So I think most of you guys have did a very good job, so I'll not go too much detail of that. So we're building the linear relationships of using the variable to predict y. So you have to know that how good is your model. So first of all, we check what you call statistical significance, so which is the p-value, and then we have to check what is called practical significance, which is the r-square. Of course, I mean, in order to measure how good is your model, we have other parameters such as adjusted r-square and also some measure of the information that we gain, which we call AIC and BIC. So one of the things that is very important is the higher for the r-square, and that's better for your model. However, on the other hand, for AIC and BIC, is the lower the value of AIC or BIC, which means the better of your model. So you should really pay attention to this. Just don't get confused with the R and R adjusted r-square are pointing up, and AIC and BIC are pointing down. And so we're building a model using the LM function. And so I guess one of the common questions is asking you, how do we interpret the coefficients associated with your model? And also you have to check with the p-value to see if that's statistical significant or not. So that's for the general the question. And also you learn that we have to, what if a two variable has like interaction? So we build our interaction term to see that's model equals to LM while tilde x1 times x2, which means that we're not just having their isolated effects, but we also have their when they're together. So this is what we call the interaction term. And so the last part is transformation and dummy variable. So first of all, what is transformation? So when we got the data, we check their violence of the assumption, such as if there is some nonlinearity there, or if there is some violation of the normality. So we can make the model better by transforming the data. Very common ways do we take the log, or we take the square root, and we transform the y. But also you can transform x, or do log y versus log x at the same time. But the one thing you have to pay attention is always checking, plot your model, checking if the assumption has been improved, if the model has proved that. So that's so that's about a transformation. And also we talking about dummy variable.
Sorry to interject. I just realized I didn't say at the beginning concepts, and then we'll do practical models.
Thanks. Yeah, and with dummy variable, so we saw a lot of in the homework. So which like for example, like if you have a home size which is large, medium, and small, so you not do it with numerical, you encode it with as a dummy variable 0, 1, 2, but the 0, 1, 2 is not numerical, which means that order doesn't matter. So when you deal with dummy variable, you're building your model, and so dummy variable allows you to build different model for the different category. Say we build with the home size problem, we build a model for when home equals to large. We build a model for home equals to the size equal to medium, and we build a model for size equal to small. So we treat them differently, and this is assumption. So its short notation is line, which is stand for linearity, which means that there are linear relationships between y and x, and independence, which means that data points are sampled independently, and we don't. It's hard to see from plots, but generally for multi-regression problem, we assume that the assumption is not violated, and also we know that a lot of time we might have some issue with the normality, which is the normality of the residuals. And also the last one, the equal variance, which means that if you see on the plot, the variance of the residual should not change with the x or the phi value. So which means that if you see the plot horizontally, they should have the same trend. All right, so that's the basic of multi-regression. Any problem? Good. So that's what we learned from the second midterm. So now we are talking about some of the new concepts we learned for the past 3 weeks. Good question. So logistic regression. So logistic regression is actually very similar to the linear regression, but the point is now we see that dummy variable. We see a dummy variable in the linear regression that sometimes x is not treated as a numerical, but now the y, the object you want to predict, is not a numerical. It is now a binary value. Well, you can say it's numerical, but so the order doesn't matter. So it's a binary case, yes or no, or cancer or healthy, right? So instead of just directly predicting y, predicting 0, 1, we try to predict the probability p associated with that. And so p over 1 minus p is the odds. And we take the log of odds. Now we create a linear function. Now we go back to what we learned from midterm 2. So log of odds is a linear function of the variable. And we learn about the basic function. So model equals to GML, not LM. So GMLs, generalized linear model. And y, tilde x1 plus x2, and data equals to data set. This is the same as linear model, but the family, you have to specify the variable for family. Family now a binomial, because we're predicting y, which is the binary case. And we call it predict. You can call predict or predict.lm, glm. And first variable is model. Second one, create a list, assign new value for the x1 and x2. Now pay attention to the red mark. So x2 is the quotes is true in the quotes, which means it is a dummy variable, right? It's not the same as the x1, which is just the pure numerical. So, and then also you have to specify the type. Type equals to response, which means that we're gonna predict the probability associated with that, which is we're gonna generate a p, which is a value between 0 and 1. And the last part, when you predict your model, you generate the probability, but we don't want the probability. What we want either yes or no, right? So how do we do that? We're gonna transform. So we call the predict function and compare with 0.5. So any probability larger than 0.5 is gonna to say yes. And any value which is less than 0.5 or less or equal than 0.5 is gonna to be predicted no. And also, well, in the test, we may asking, okay, how are we gonna interpret the coefficients? So say, okay, a simple model, y is a function of x, just x. So if x increases by 3 or by 3 units, if I ask you what the log odds is going to increase, the increase should be 3 times the b1. b1 is the beta 1, the coefficient associated with x. But a more tricky question will be the odds. How much is it going to increase? Well, it's going to increase by e to the b1, which is the coefficient, times 3 minus 1. Why is that? Because if we increase x by plus 3, because we have 3 times b1, so the odds nu is going to be odds O times e to the b1 times 3. So that's the expression. And some of the basic concept, how good is the model? So generally we cannot apply for R square, but we have pseudo R square. So if you type, when once you build a model, you type summary model, and you can see the null deviance and the residual deviance. The null deviance is when you're building a model using none of the variable, just using a constant, or you call it intersect. And residual deviance is your actual performance of a model when you're including some of a variable. And pseudo R square is constructed by 1 minus residual deviance divided by null deviance. And so we had to actually estimate how good of our model, not just by the pseudo R square, but by actually how it can predict correctly, right? So we have to have a base model or reference model, which are called naive model. Well, this model actually don't need to call any function, build any model. So just simply, we just predicted the most common outcome. Say if you have 100 yes and 50 no, and total number of 150 data points, we just predict, okay, all of them to be yes. And we got the roughly good, accuracy. So that's the idea of the naive model. You don't have to build anything. So a simple way, just using table and put the data sets in that, and you can know how many yes you have and how many no you have. So last part, we're building our model, and we're gonna count how many predicted yes we have, right? And then also we count how many actual yes we have. In the homework, I've been asking, okay, so in this case, the yes has been encoded as 1, no has been encoded as 0. But in homework, sometimes the raw data is just yes or no, or health and cancer. So you cannot, if you haven't converted to yes 0 or 1, you have to compare with the actual yes. So I guess my suggestion would be just when you're in a test, definitely checking your data sets. Make sure they have been, the correct value of them. All right. And last one is just sum. You compare with your predicted yes with the actual yes. If they match up, you're getting true. If it didn't match, you're getting false. And when you sum how many yes you have, how many corrected prediction you have, and divided by the number of row, which is the number of the data points. So now you get the ratio. Once you get a ratio, you compare with the ratio given by your naive model, which is actually just a portion of the most common outcome. And you will get to see if your model actually performs well, performs better or not than the naive model. Any question? No.
I'll just take a minute to try to put the screen down as well so that you guys can. Next we'll go to time series. So time series can be considered as an expansion or an extension of your multiple linear regression, in the sense that while multiple linear regression has many predictive variables that are independent of each other or may not be independent of each other, the main idea about time series is that you're predicting y based on existing lags of y. That is, you're predicting a future point based on the data that you already have, your past data of y. So obviously, the most the clearest violation of your line condition would be that of independence in a time series data, where you have autocorrelation in your lags. So for example, lag 2 and lag 1 may be more autocorrelated than say previous lags. So that's a clear violation of independence, and you can observe this by plotting, say, a plot against y and lag of y to 1. And if you see some kind of a linear trend, you can say that y is autocorrelated with lag of y. The main functions that we will be using in time series is the TS function to create a time series object from any given data. So the TS function is one such example. The example that we will be seeing is a built-in data set, so you don't need to convert that to a time series. So at times when you have already a time series object, you don't need to convert them. The second one is a lag function to calculate the lags from the data. If I have y, I can just put lag of y comma minus 1, and that will give me the first lag, or depending on how the data is. The third is the ACF and the PACF functions. So these functions basically plots the ACF and PACF plots for you, and the blue dotted line is the level of significance. Any spikes beyond these blue dotted lines up and below, you can say that those lags are significant. The fourth one is the ADF test, the augmented decay-Fuller test, for determining whether there is stationarity in the model, in the time series model that you create. And so the ADF test has a null hypothesis that the data is not stationary, and an alternate hypothesis that the data is stationary. So whenever you get a p-value of greater than 0.05, that's when you know that it is stationary. And okay, so the next is models. We'll be looking at the moving average models. We'll be looking at exponential smoothing, the SES command. The simple exponential smoothing model does not take into account any trends or seasonality in data. The second one is a Holt model, which considers trend in data. And the third one is the Holt-Winters model, which is the HW command, which takes into account the trend and seasonality that's in it. Okay, so next would be simulation in Jared.
So for review, I've got the, right now this says ask a question. I don't think we have that working right now, but anyway, you can raise a hand to ask a question. I don't know if we can get that to go away or whatnot, but so for simulation, the gist is sometimes we have decision processes or steps of decisions and actions and randomness that's too complicated for a decision tree. Or maybe we want to know something beyond just the expected value. What if we want to know what the probability of generating a profit is given a specific business model? Kind of like in your homework, right? You don't have a probability question there, but you could do that with investments A, B, and C. So instead of making probability tree, or a decision tree, excuse me, we simply run the situation thousands of times. And that'll give us a distribution of the outcome. And from there, we can take means or standard deviations or find probabilities based off of the 10,000, 100,000, or a million samples. Usually we use this with the simulate command in R. Some of you may have learned how to use a for loop. That's great too. The code, no matter if you code it correctly, it'll give you the same answer. And so we'll practice this code later, and there's really no substitute for practice because I really can't review more concepts than these until you actually get down into doing it. Any questions in general? Great. Well, we'll practice this later.
So we'll start with the examples. The first one is on probability. I'll be handling conditional probability and Bayes theorem and joint probability.
There we go.
So the question for you is 25% of male students and 13% of female students in a class are left-handed. Assume the class has 40% males and 60% females. I select a person at random. What is the probability that they are left-handed? And if you're done with the first question, the second question is an extension of it. You just use the first answer as one of the terms in the Bayes theorem that you solve for the second question. So you can do that as well. I'll have to use the board here, so I'll pull this up for a minute. So the first question is that 25% of the male students and 13% of female students are left, which means probability of left given male equals 0.25. Probability of left given female is 0.13. And then you know that probability of male students is 0.4. probability of females, 0.6. So how do you calculate probability of left? Anyone? Yes.
Probability of left-handed given male.
Uh-huh.
Probability of male plus the probability of left given female. And
Probability of female, right? So probability of left given male times probability of male plus probability of left given female times the probability of female. That's going to give you an answer of 0.178. And if you got that one right, you can substitute that to the denominator of your base formula to get the second answer. So that would be probability of, what is the conditional probability? The person is female given that they are left-handed. So female given left-handed is probability of left given female times the probability of female by the probability of left. That's going to give you an answer of 0.438. And the last question is, if the class has 100 students and 30% of them, so do know that this is an extension of the first two questions. So you still have 40% males and 60% females in the class. So now the class has 100 students and 30% of them are juniors. The rest are seniors. And 5% of the class consists of female juniors. What is the proportion of the class that is either a junior or a female or both? So you use the union and intersection as a formula for those. So the probability of unions is individual probabilities minus the probability of intersection of those two. And you're going to get an answer of 0.85 for that. Any questions?
What was the answer for the second one again?
The second one was 0.438. Any questions? All right. We'll move on to decision tree example. Jared, just go. While I would screen. You're gonna need the board, right?
You can switch sides.
Sorry.
You can switch screen sides.
Okay.
And projection on this one. Wow. Oh, thanks. What do I have to push? Oh, PC. Gotcha. All right, so decision trees, right? So you're an investor who flips real estate, and you really need to know if houses have major issues. So this is a simplification of a common flipping model, or at least flipping business plan, fixer-upper style. So you buy a house for $100,000, remodel the interior, and you can sell it for about $150,000. So you need a fair amount of capital to get started. You invest $20,000 on top of your original $100,000 investment, and you get $30,000 profit. All right. Great thing is, it only takes about a month. That's pretty good for a single house in your business. However, if there's issues with the foundation, you're going to have to pay something like $45,000 to fix the foundation too before you can actually sell this house. What's our expected monetary value for a single transaction, or for a single purchase and resale of a home? Give you 3 minutes. If you need more, let us know. Okay, let's talk through this. This you can find with a fairly simple decision tree. When a decision tree is simple, I know I would be, you could be tempted to skip steps and to not draw the tree out and just figure you can calculate in your head. Maybe you can. Caveat there is, if you come across a more complicated tree that you need to evaluate, that's harder to bookkeep in your head and keep the different components straight. I would highly suggest drawing it out, all right, with explicit details, squares and circles, the whole 9 yards. I don't know, we call it that, probably should be 10 yards. But square nodes, if you recall, represent decisions you get to make, all right? Not all of these splits in this tree are decisions. So the first decision you have is what? To buy the house or not. All right, if you don't buy the house, your monetary outcome is 0. Nothing happened. Sometimes that's a safe investment. All right, if you do buy the house, what's the next thing that happens down the line? By the way, any house you buy, you're going to remodel the interior. So that $20,000 there always happens. Okay? The next thing to happen is, what do you find out? Foundation issues. All right, we're going to draw a circle because that's a random node. You don't get to choose if there's foundation issues. In the real world, hopefully you knew something about that before you bought the house. In our simple scenario, you don't. All right? So, 2 possibilities with foundation issues. Either you have them or you don't, right? So we're going to say up is issues, down is no issues. What's our financial outcome if we have issues? Actually, let's start with the no issues. That's probably a little bit easier. Right, off the bat? Correct. But the full calculation is, let me write this a little bigger. Off the bat, we put in $100,000, right? On top of that, we paid out 20 grand. New wood floors, new sheetrock, new paint, new cabinets. Hopefully, at the end, we sell it for 150, and we make 30 grand, right? Okay. If there's issues, we have all the same numbers, but what? We also have to pay to fix the foundation. That ain't cheap. And we actually come out $15,000 in the hole. Okay. What else do we need? Probabilities. We have a random node here, which means the probabilities are going to split, right? Or the probability is what causes us to even split here on this random node. What's the probability of having issues? 0.2, no issues. 0.8, that doesn't look like an 8. All right. So we started from the left side, chronologically move forward to our leaves, right? Building the probabilities in the process. Now what? We work from left to right, and now we work back from right to left to calculate our expected values at each of the nodes. So our expected value at the circle, 0.2 times our unfortunate outcome, plus 0.8 times our ideal outcome, comes out to $21,000. I didn't do that in my head, I did it beforehand. Right? All right. We calculated the value, the expected value of a random node by calculating the expected value, multiplying the probabilities times the value plus this probability times that value. Okay? So weighted average of the outcomes weighted by the probabilities. Now what? Now we make a decision. Which one are we going to choose? Probably the 21K, right? Otherwise we wouldn't be in this business. Good news is you do enough houses, you can afford for some foundation problems. All right. Any questions on filling out a basic decision tree? What if this is a little more complicated? What if we had lots of branches? Let's say this actually started out over here. Right? We had some other decision and some other random occurrence. And this is all just a branch down that tree. What would change? Would our monetary values at the end change? Not necessarily, unless we made a monetary decision up front. Would our probabilities change? Yes. Everything that happens here, right, those would be conditional upon whatever random event happened here at the circle. Okay? Everything on the right is conditional on everything that happened on the left. Problems in this class typically only have 2 possible random nodes, so you don't have to worry about multiple conditions. Great. But that's my warning note, right? So be careful. Why? Well, quite frankly, if you've ever looked into real estate, you can have someone inspect the house before you buy it. So let's say you can hire an inspector. Typical house inspector in the Austin area costs $300. I made up these probabilities. I hope they can find foundation errors fairly well. Let's say the inspector finds the issues 80% of the time when there are issues. And if there's no issues, they find no issues 99% of the time. In other words, the inspector is a bit of an optimist, probably thinks there are no issues, leans that direction. Perhaps he should be more cautious, but this is what we have. I want to connect this to the probability principles that Cy just talked about. All right? What's A given B? The probability the inspector correctly identifies the existing foundation issues. You don't need any math. 80. Right, 80. right? If there's foundation issues, so B is existing foundation issues, right? Notice the statement here, existing foundation issues. So that's given there's foundation issues. What's the probability of the inspector correctly identifying them? That means A is the inspector finding issues. Why am I not going to say that's the problem? A is the inspector being correct. That would make this statement the same, right? The probability the inspector is correct given there's existing foundation issues. Inspector being correct is not an event, right? That would be conditional. The inspector saying something is the event. So the inspector saying that there's issues and there's actually being issues means he's correct. Inspector saying there's issues and there's not actually issues, he's not correct. But the correctness is a function of two things, what he said and what actually happened. Okay? Why do I bother to mention this, especially when I'm not the one who's had the probability slides, is because on these type of problems, that's a common mistake. Okay? And the whole point of the following statement. What is P of A, right, given not B? In words, this is the probability of the inspector finding issues given there's no issues. Okay? Now you can take Bayes' rule and solve that. Hunky-dory, you already had some Bayes' rule practice, right? So we'll forego that for time's sake, unless you really want to see it happen. Maybe some of you do, so this is what it is. Right? You can fill in those pieces as needed. All right, for time's sake, we'll keep moving. Any questions? Yes, please.
So when we would draw it out, if you were doing with the investor, it would be you'd start with the decision to hire or don't hire, and then a circle for the investor. Or sorry, if you do hire the person.
Okay, I'm just drawing this part of the tree small because this part of the tree is always the same. This is just a house problem, right? You can buy the house, yes or no. If you say yes, it can have issues. So maybe I should use a different color. Notice that this part of the tree is the same. No matter, wow, I'm erasing. I take skill. That's even more erasing. All right. Sorry, Hunt. So here's our original tree. This happens, this would be the tree. The numbers will be different, but the same structure is there, whether we take his advice, the inspector, right? This is the inspector's advice. If we take his advice, the tree structure is the same. If we don't take his advice, the tree structure is the same. If we don't even talk to him or pay him, the tree structure is the same. The difference being we now have this decision and a random event, and then based off of that, we now make the house judgment. Does that help? So this is what it would look like. I'll put the black back on the board because evidently the blue markers erase the black markers. Okay. As I said at the beginning, we could go through and do all the math for that. Examples on how to do that are available on the online video for session 1 for exam 1 review, and that takes a while, so we're going to focus on the more recent material, okay? So this is the type of question you would have. Does it make sense to hire the inspector? The subsequent question is, what if he was perfect? Perfect information simply means this is 1. That's all that means. Okay? Subsequently, the probability of him being wrong, right? That's marked there. Probability of him being wrong is 0. Okay, back to the correctness thing. This means the inspector is always correct. But to your question, that doesn't change the fact whether it's going to have issues or not. That will still happen at the same rate. So the trick there is actually, after the inspector, what's the probability the inspector says yes or no, is the probability originally without his information having issues. Right? Because there's still a 20% chance there's issues. There's still an 80% chance there's not issues, he can't change that. But the conditional probability is later will be perfect. Okay? That's my very brief coverage of perfect information. I'm happy to take your questions after class too.
We'll move to an example on multiple regression. You can load the state dataset from the GitHub page. The first line of it gives the same thing. You can look at your student code and you'll find the same thing as well. Now, what I want you to do is I want you to view the data set and see for yourself which all are the numerical variables and the categorical variables. I want to predict income based on a certain variables. So first, I want you guys to run a multiple regression model to predict income from all numerical variables and determine which variables are significant, statistically significant. So you can ignore all the categorical variables that are present in the data. I just want to predict income from all of the numerical variables. As you know by now, that is an LM statement. So I'm viewing the data set here. It has all 52 states and the population in each of them, the income levels, the illiteracy rate, life expectancy, murder, high school graduates, I guess, frost area, size, and crime. So you can ignore obviously the state, you can ignore the size and the crime for now, and predict income based on everything else. So that would be the LM statement over here. It's the full model. Income against population plus illiteracy plus murder plus H's grad frost area. Data equals state. Run that and print the summary. This is not really a great model, but so how do you determine statistical significance?
The p-value.
P-values, right? So you can see that two predictor variables here, population and H's grad, they're not like greatly statistically significant, but they still are. So I'm going to include those in my model. And the next thing that I want you to do is to run a reduced model, having only those significant predictors and determine the R-squared for them. I know this is a routine exercise, but
Would life expectancy not the bad thing?
I guess not. Ah, right, okay. I think I forgot to add that one. Okay, I'll run the model again. Doesn't seem to affect, so you still have the reduced model of income versus population and H's grad, and I'm running the summary of that model now, and that gives me an R-squared value of 0.4575. It's not a great model, but I just want to use it for demonstration purposes. Right, okay, so next what I want you to do is I want you to predict the income given a population of 300, I guess it's thousands, I'm not sure, and H's grad is 46. and give a 95% confidence interval for your prediction. So this is using the reduced model. So I'm going to be using the predict statement here. So first you specify which model you're predicting the result on, which is model 2 for us, and give a list of all your predictor variables that are present in the model. So population equals 300, HS grad equals 46, and I want to also print a 95% confidence interval. So interval equals confidence. If you do not specify the level, it defaults takes it to 95%. So I'm gonna predict now. So that's gonna be my fit. Fit's gonna give me the actual value, the predicted value, and the lower and the upper bound for the 95% confidence interval is printed along with it. Any questions? Yes?
Will you post your R script after this?
Sorry?
Are you gonna post your R script after this?
Yes, of course. I think it's already posted as well.
Okay.
Any questions? Okay, so we'll move on to multiple regression with interaction and Han will take over.
So yeah, please go ahead and load the Boston dataset. And so we have a main variable in the Boston dataset. So I just want you to build using LSTAT and age to predict the MED, which is the minimum value of the house. And so once you build a model, what's the R square? I think that's should be very straightforward. I'm just speed up. So then, second one, once you load the data, you build LSTAT and age, and then I want you to build a model which include the interaction term, and let's see if the R square has been proved or not. All right. So So we are building our first model, which using LSTAT and age without the interaction. And let's see. So the multiple R squared is 0.55. And if we include interaction, which is LSTAT times age, and we're building our second model, and our R square is a little bit increased. And then we can also calculate their AIC and also or BIC, just using AIC for our second model, and definitely can calculate for the first model. Right. So I want you to predict the MEDV given L stats equal to 10 and age equal to 80, well, since I guess all of you know how to use the predict function, so I want you to just calculate by hand. So how do we do that? Well, since we're building a linear model, so we can do is from the summary model, we know the coefficient for intercept, we know the coefficient for L stats, we know the coefficient for the age, and also for the interaction. So we take their value, right? And we define the first variable is LStat1, which is equal to 10, and age equal to 80. So we take all of the coefficient and we construct the equation. And using that, we can calculate the predicted MDV, which is that. And also we can try using just, I haven't built in the model. Okay, model. Alright, so let's give you a same value, but the point of trying to make it is you have to understand what is happening when you do the predict function. It's just taking all the coefficient and plugging the value you define for your predictive value, and then combine them together. That's your predictive value. The last one, just taking all the variable. So using all the variable and building a model and calculate the R-square. And also calculate how many variables that are statistical significant given alpha equals to 0.05. So a simple way is just meta value telltale dot, which take all the variable. And once we build in the model, taking all the variable, and we see that R-square has been improved. Previously was just 0.55, now has been increased by 20%, which is 0.73. And so we count that, we know that, so this is all the variable, and by given the alpha equals to 0.05, so we have total of 9 variable, that which is statistical significant. And just one thing, when you calculate the variable, do not include the intersect, because that's not a variable. Any question? So let's move on to the over-linear from the past 3 weeks. Just regression. All right. So go ahead and load the grad school data. So the grad school data, the data connection of the student apply to one grad school. Let's say just our grad school of business at UT. So go ahead and load the data, and let's view the data and see what we have. So we have 4 variables at mid, which is either 0, 1. 0 means that you got rejected by the grad school, and 1 means that you get it offer. And GRE means that GRE score, which is a scale from 220 to 800. And you have a GPA, which is your undergrad GPA. And you have a rank. Rank, you see that's a numerical. Actually, we should treat it as the dummy variable. So rank is from 1 to 4, and 1 means the top is undergrad university, undergrad institute. So we're gonna using this data set to predict one applicants to see if they'll get rejected or got the offer. So first model is try to build a model using GPA to predict the admit and calculate the pseudo R-square AIC of the model and see how much the odds increase, a GPA increase by 0.2. Pay attention, not log of odds, just odds. So you have to transform. So the first model, admit is a Y, which is the binary case, and GPA is your X, and data equals grad school, and family equals to binomial. And let's see the summary. From the summary, you know the null deviance is about 500, and residual deviance a little slightly lower than the null deviance. So if you take these two values and put them in this in the equation of pseudo R-square, and you can calculate that, which gives you a 0.03, which is not a very good model. And also the AIC, just call it AIC using your model. So how much does the odds increase, GPA increase by 0.2? So using the equation, so e to the 0.2 times the coefficient before the x, before the GPA. So from the summary, we know that GPA, the coefficient for GPA is 1.05. So the increased odds is e to the 0.2 times 1, then minus 1. So that gives you a point. It's about like 23% of increase if your GPA increased by 0.2. So then I want you, because we know that the pseudo R-square is not good for the first model, so I want you to build a model using the rest of 3 variables: GPA, GRE score, and rank. But I want you first transform the rank to a dummy variable. So how do we do that? We have a factor function, so we can using factor function to transform a rank. And I want you to do the prediction given GPA, GRE, and rank score. So let's go ahead and do that transformation. So first of all, you're going to transform the rank to a dummy variable calling the factor grad school rank, and assign that rank value.
Why don't you use the if else instead of the factor to transform the dummy variable?
Why not use
If else, the R code.
The assumption works great if you're putting it into only 2 categories. In this case, factor I believe has 4.
Four, yeah.
Your school, or what's it called, rank variable has 4 levels. Factor will take those and convert it to A, B, C, and D basically. They'll still call it 1, 2, 3, and 4, but R will know that it should be interpreted as a categorical.
Will
Yeah.
factor still work for if it just has 2?
Sure. 2 to 100.
So once we transform to a dominant variable and we're building our model using GRE, GPA, and rank, let's see the summary for our model. You see, and so we have GRE, GPA, but now we have 3 other additional variables, which is rank 2, rank 3, and rank 4. So rank 1 is the reference level. So rank 2 can only be 0, 0, 1. All right, so once we build a model, I want you guys to predict the probability of admission given GPA equals to 3, GRE equals to 880, and rank equals to 2.
So we don't put the family equals binomial on this one. That's good.
Oh, I think it's, yeah, we should. Let me rebuild the model. Okay, cool. So, how are we gonna predict GR? So we're gonna call the predict function. It's weird.
Yeah, parenthesis right there is type of responses inside the list. So I'm gonna move one of those parentheses right there after your quote 2.
Oh yeah, thanks. I see. Thanks. Okay, yeah. So that's the probability of get admitted. If you're giving GPA equals 3 and blah blah blah, which is the 0.38. So once we build our model, we want to know how well our model does, and so we have to we need to compare with a naive model, which is so go ahead and do the naive model. So you don't have to even build a model. What you need to do is use table. So table, grad school, admit. So 0, rejection is about 300, and offer is about 100. So take the 2 value. So 0 is the most common group, and so take that value and calculate the portion. So the portion is about 0.68, which means that at least our model has to give a higher value than this value.
But what was the back to the prediction that we just did? What was the answer for that? So for the, what was it? GPA 3, GRE 780, rank 2.
Right. So that's
I'm getting a different
point.
answer than that. I'm getting -4.
I think you should get you should always get a value between 0 and 1.
Okay.
So maybe there's some typo there. Yeah, we can talk later if we still have that problem. Right. So that's our reference model. So now I'm gonna calculate how well our model performances. So that will be so since the rejection is the majority, so I'm gonna calculate the predicted rejected, which is by calling the predict function and the sign. Since rejected is 0, so from the reject function compare with 0.5. If it's less than that, we convert to 0. If it's larger than that, we convert to 1. So once we do that, we get the predicted rejected. And also we have the actual rejected, which is grad school, admit compare to 0. If that's 0, means that's got rejected. And then we sum by compare the predict rejection with the actual rejection. So gonna sum all this correct prediction and divide it by the number of rows or data points in the grad school. So if we do that, it's supposed to give a better model. So 0.71, which is better than the naive model. Any question?
So 0 counts as reject.
Yes.
And what does this tell us about, like, the admin side of things? Like, what do we know about the predicted admission and stuff, now knowing this stuff about predicted rejection? I'll think about it, reword it.
Okay. Yeah, we can talk about that later.
So why in the code is it less than 0.5? If, like in your naive model, it's above 0.5, it's 0.6825.
This one?
Yeah. So considering that's 0.6825, why in the code for the predict reject, why is it less than 0.5?
So when you do the prediction, you're giving the probability between 0 and 1.
Yeah.
And if we set a threshold 0.5, which is the midpoint of 0 and 1, any value, because we want to, so the larger value, if it's close to 1, we assume that we're going to predict it 1, which is the yes, or which is the, in this case, is the offer. If the value is equal to 0, so which means that there's no chances of predicting yes, so we say, okay, we predict no, which is rejection.
Okay. So if you were writing like predict.admit instead, it'd be greater than 1 or greater than 0.5. Okay.
This one?
Yeah.
The second one, actual. You're talking about the actual?
No.
The predicted statement. Okay. So if that's larger, so if you set to be larger or equal to 0.5, so you should change this to predicted offer or admit. Because we know that, I mean, in this case, we know that 1 is referred to admit and 0 means rejected. Yeah. Any other question? All right, so let's move to time series.
Alright, so we'll go to an example of time series data. I want you to load this data set called OS tourists from the FPP2 library. So this is a built-in data set to R. You don't need to take it from your GitHub page. You just install the package called FPP2 and then you run the package using the library fpp2 command, and you just load os tourists. Just type in os tourists. It's already a time series object for you guys, so you don't need to convert it using the ts command. It's already a time series. So
If you have issues loading FPP2, please let us know and we'll go.
the first thing you need to be doing is install .packages fpp2 and then library fpp2. Yes.
Okay. Can you code it? Just use codes. FPP2.
Oh. Yeah, there's
If you have any issues loading the package, please let us know. So install .packages codes fpp2 and then library.
Just
Yes, so codes.
Install packages, parentheses. Close parentheses. You might have to put one quote or 2 quotes. Two. One. Clear.
Yeah.
You just type. How do I load the? They just type.
Library.
Yeah.
Just fpp2 codes.
Just remove.
And now AUS. Just AUS. Anyone having issues loading the package? So after using install packages fpp2 and library fpp2, I want you to type in os tourists and just press command enter and you will view time series object. I want you to understand what the data has really looked like. So I'll do that over here. I don't think I have it. I'm not sure. Give me a minute. Yeah, it's already installed, so I'm not using the install.packages over here. I just directly used library fpp2 and then os tourists. Perfect. So this is the data set. So this is basically numbers on the number of tourists arriving in Australia from the year 1999 to 2015. It's preloaded to R, so that's why you use the library fpp2. Okay, perfect. So first of all, I want you to compute the lags of 4 previous years of data. You might observe here in the data that you actually have quarters, quarter 1, 2, 3, and 4. So if I put a lag statement of, say, lag 1 equals lag of os tourists, comma, minus 1, it's going to get me to the previous quarter and not the previous year. But I want lags for the previous 4 years of data and not the previous 4 quarters. So how do I do that? To compute 4 years of lags, I type in lag of air, comma, minus 4, minus 8, minus 12, and minus 16. That's going to give me a yearly lag as opposed to quarterly lag that 1, 2, 3, 4 is going to give me. So I will run those statements now. Air 1, Air 2, Air 3, Air 4. Okay, perfect. So I need to So I'm just converting that Oster's name to air. I don't know for what reason. I just copied the code from one of my sessions. So yeah, now the Osterist is going to be simplified and called as air. And I'm computing the first 4 years lags, right? That's all I've done. And that's how you deal with quarters in the lag statement. If the question asks you for 4 quarters of lags, you just put -1, -2, -3, and -4. But since I've asked for 4 years of lags, we change that. So I want you to now predict the air passengers in a year from 4 most recent years, the lags that you've created right now, by running a simple linear regression separately on the 4 lags. So I want you to run air against air 1, air against air 2, against air 3, against air 4 separately. And I want you to run the ACF function of air and compare.
Can you show your lag code again? Thank you.
That's the code for the lags. I want you to run simple linear regression models on all 4 lags separately.
On the exam, will the stuff already be like moved to time series data, or we're gonna have
You might need to convert it to a time series data. So you can use the TS function. I think plenty of examples have been given in your slides and the R session codes. I'm not going to be handling that today, but you can find plenty of information on that. So running a simple linear regression, I'm just running simple model 1 of air against air 1, getting the summary of that. You can see that air 1 is a significant predictor in the sense that air can be predicted significantly by air 1, which means that there is significant autocorrelation in the first lag. Similarly, for simple model 2, air against air 2, you can see that the p-value is quite low. I know it says it's essentially perfect fit. Summary may be unreliable, but you can go on. That's just a warning. But you can see that it's autocorrelated again. So the second lag is autocorrelated with the future data, whatever you're going to predict, right? So again, simple model 3 against air 3. Again, you can see that it is significant. And simple model 4 against lag 4. You can see that it is significant again. All right. So I want you to understand what the ACF and the PACF plots do. How are they related to simple linear regression and multiple linear regression? So the ACF plots is a plot basically deals with exactly this, the simple linear regression of lags run separately, right? So, sorry.
That better in the back.
Can you see it better now? So ACF of air, I'm going to run that. Okay, figure margins are too large. Okay, all right. I've run the ACF statement over here. So what can you observe in this ACF plot? I want you to look at lags 1, 2, 3, and 4 and the spikes that correspond to those lags. They are all above the blue significant line, which means that the first, second, third, and fourth lags are significantly correlated, right? Is this consistent with whatever summaries that you printed for your simple linear regression model? You did see that all those p-values were quite small, and it did say that these lags, all these 4 lags were significant. So this is what the ACF plot does. The ACF plot is basically simple linear regression models run on all lags separately and seeing if these lags are significant. So you can see that the plot is consistent with whatever summary statement that you printed. Now, extending this to multiple linear regression. Now I want you to bind all these 4. Okay, so I want you to run a multiple linear regression on all 4 lags at the same time and compare that with the PACF plot. The PACF is nothing but a partial autocorrelation, which is sort of like a multiple linear regression. I'll get to it, why it is. But I want you to run. So before that, I want you to create a data set that binds all your variables together, all the lag variables together. And using the cbind statement, you're going to bind all air 1, air 2, air 3, and air 4 into a single data frame. That can be done like this. Data set equals cbind of air. I don't know, you don't need to put air equal to air, just air would be sufficient. Air 1, air 2, 3, and 4. That's going to give me a new data frame. You can see here that everything is in a single data frame now. Yeah.
So how do we get the air data?
Oh no. So I just renamed I renamed the Osterus dataset to air because it was simpler
Okay.
using it. Osterus and then air equals Osterus. So yes.
Can we just, you know how you plotted the ACF of air, and then we can see each lag individually? Can we just do that instead of what you did previously, and getting summaries of each one to know whether it's significant or not?
Yeah, you can just print the
Like,
ACF
is
plot.
there a shortcut?
Yeah, the ACF. I just want you to understand what the ACF plot and the PACF plots do, and hence I printed the summary statement. But the ACF and PACF plots would be sufficient. Yes. I'm sorry.
Why did you take quarterly lag?
I did not take quarterly lags. I took yearly lags.
Oh, are you?
These 1, 2, 3, 4, and the ACF plot, they are yearly lags. And can you see that there are 3 spikes in between? So this is the first quarter, second quarter, third quarter, and fourth quarter. Or rather, first, second, third, fourth, and then your first year lag, whatever that is, right? So. And always remember that when you plot the ACF plot, your lag 0 is going to have a perfect correlation of 1 because any predictor against itself is a perfect correlation. So that's all. That number is always going to be 1. Right? Okay, so if you run the multiple linear regression model, I want you to run the multiple model LM of air against air1 plus 2 plus 3 plus 4 using the new data set that I've created by using the cbind command and printing the summary for that model. Okay, before going to the PSCF, I'm going to show the plot. Okay, so how do you interpret this multiple linear regression model? What do you see from the p-values here? Which lags are significant? Okay, yeah, so see these significant codes over there? 3 stars would imply significant at 1% level. 2 stars at 0.1% level. 1%, 5%, 10%, and nothing for 1. So you can see here that air 4 has nothing, which means that it's not significant at all. You can see that air 3 has 1 dot, which means that it's significant at the 10% level. You can see that the other 2 are significant at least at the 0.05 significant level, which means that if I have 2 stars over here, if it's significant at the 1% level, it's obviously significant at the 5% level as well, right? So the PACF plot that I'm going to plot right now, it does exactly this. So it makes all the other lags constant, and it's going to find the effect of one lag, keeping the other lags constant, right? So I've already done it. I'm going to show you how the PACF plot looks now. What can you observe from the plot now? Remember, however, that the blue lines up and down, they correspond to a 5%. And how many variables were significant at the 5% level? Lag 1 and lag 2 were significant at the 5% level. So air 1 and air 2, these 2 were significant at the 5% level, which explains why this spike and this spike are beyond the blue line. You do see that the third lag was significant at a 10% level, but unfortunately you can't see it over here because your blue line's for a 5% significant, right? So that's about that. So you can see that the PACF plot again agrees with whatever summary statement that you printed from your multiple linear regression model. Any questions? Yes.
So the last 3, 4, 1,
Oh, yeah. So these blue lines, they correspond to a 5%, right? And I showed you from here the significant codes, right? That only these two were significant at 5%. This is significant at 10%, but not at 5%. So this spike is still not going to reach the blue line.
that's because you bind them together, right?
Yes.
Because another in the previous
Yes, exactly. Exactly. So when you run, so that's essentially the difference between a simple linear regression model and a multiple linear regression, right? Individually, all your predictors can be significant, but when you put them together, some of the predictors won't be significant. So that's exactly what this done here. When I predict add against add 3 individually, you can see that it was significant at the 5% level. But when I put them together using all the 4 lags, you can see that it's not significant.
PACF is for multiple regression.
Yes, PACF is for multiple regression, and ACF is more like simple linear regression done on lag separately.
So this is saying that lag 2 is significant, including all the predictor.
Yes, yes. Any other questions? Okay, so next I'll go to stationarity of data. I want you to run a test to examine if the Osterus time series is stationary. Remember that ADF test is the test that we use, and ADF dot test is the command. Give you a minute to run the ADF test statement. Okay, so the ADF test command is under a library called T-series. If you already haven't installed that package on your laptop, you might need to install it using install.packages. After you do the installation, you can just run library T-series and ADF test of air. I'm running those now. Okay. So the augmented diffuser test is a test for stationarity. You can see over here, you actually don't need to remember the null and the alternate hypothesis, because when you print it out, it does say that the alternate hypothesis is stationary, which means that the null hypothesis for the ADF test is that the data is not stationary. And what do you observe from the p-value? The p-value is very high, which means, which one do you accept when the p is high, greater than 0.05? You fail to reject the null hypothesis, right? So whenever your p-value is less than 0.05, you accept the alternate hypothesis, and when it's greater than 0.05, you fail to reject your null hypothesis. Which means here that because the value is 0.8919, that the null hypothesis holds true and the data is not stationary. There are differencing techniques that can be applied to resolve stationarity. I'm just going to run one of those commands. Diff. This is called differencing techniques. If I just put saying a diff of air, right, and run this, it's going to basically difference data with respect to quarters. So quarter 2 minus quarter 1 is going to get added to this one. So it's just like one lag. And when I run the ADF test on diff of air, oh, okay, it went somewhere else. Give me a minute, sorry. ADF test of diff of air. You can see that the p-value has gone below 0.05. So now you can say that this time series object is stationary. So differencing is one of the techniques that you do apply to solve for non-stationary data. But I don't think you guys did that in your lectures, so just consider this as extra information. Yeah, so next what I want you to do is I want you to forecast Osteurists using a simple exponential smoothing model, a Holt model, and a Holt-Winters model. Remember that the simple exponential smoothing model does not take into account trends and seasonalities in data. The Holt model takes into account the trend in data, and the Holt-Winters model is the more complete model. It takes trends and seasonality into data. However, what I'm going to do first is I'm going to plot Osteurists first for you to understand. Okay, the margin. Okay, so what all can you say that is present in the data based on this plot? Do you see a trend? So there is an upward trend, right? And do you see stationality? Oh, sorry, rather seasonalities. So what is a seasonality? The up and down spikes, they indicate seasonality in data, right? So you do see that there is a trend and there is a seasonality in the data. So which model of the three do you expect to predict Osteris best? The Holt-Winters model, right? So that's what you'd be expecting, and that's what's going to be happening as well. So the exponential smoothing models can be run using the forecast library and library of forecast. Okay, and I'm going to create a new time series, new object for the SES model. So SES of air, alpha equals 0.5. Alpha, beta, and gamma are parameters for your exponential smoothing models. You can refer your slides to know what these parameters exactly refer to. But if you do not include alpha, beta, and gamma values, R is going to find the optimal alpha, beta, and gamma values for you, which will be a good thing. So in case they haven't specified in the question as to what alpha, beta, and gamma you should be taking for your models, you can just leave that blank. You can just say SCS of air, Holt of air, and HW of air, whatever it is, right? So have included over here. So I've run the model, the plot. So what do you observe from here? Like I told you, a simple exponential smoothing model does not take into account trend and seasonality. So you just see a flat line over here, which is a really bad forecast, right, from the previous years of data. So, and now I'm going to run a Holt model. Holt is what the command is of air. Alpha equals 0.2, beta equals 0.1. You can ignore and see for yourself what happens. You're going to get the same result. I'm going to plot that. You can see now that there is actually an upward line. So the model has taken trend into account, but still seasonality is missing from the forecast. And the best for this data is to use the Holt-Winters model and specify alpha, beta, gamma parameters and plot that. So does this look more of a forecast than the other two models? Better. Okay. You have questions? Yeah, it's going to be uploaded to the GitHub page.
I mean, you're going to do that before the next session or after that?
Probably today. Yeah. That's perfect. So you can see that for this data, the Holt-Winters model explains best. Okay. I'm going to go to the next topic now. Jerry? He'll be taking simulation. You can run the example. You run a used car dealership. Yes.
Questions on time series? No. Yes?
Very nice. Time series. You need first plot the time series to understand this seasonality.
You can start running this one.
All right, so back to simulation. We'll wrap up today probably with that. We've got 10 minutes. We can stay a little after if you got questions. So for this example, you should have this code, right? Get this from the code set. Great. You got to fill it in. You're running a used car dealership. All right. So you have three things you really need to do. You buy a car, you repair it, fix it up, detail it, clean it, wash it, repaint it, whatever you need to do. And then you try to resell it. Okay? So particularly, you buy the car anywhere from $12,000 to $18,000. We'll call that uniformly distributed. You do anywhere from $0 to $1,000 of improvements. We'll also call that uniformly distributed. And you sell them from anywhere from $15,000 to $20,000. For the sake of the example, we'll have that also be uniformly distributed. Anyone not heard of a uniform distribution before? Pretty straightforward. It means every value inside that range has equal probability. Every value outside of that range is impossible. So instead of drawing a bell curve, it's a block. All right. So if you looked at the practice test, you have a question that's a lot like this. So I have even more blanks than they do. Take a couple minutes, see if you can figure that out. I'm just going to get out of your way because I'm standing in front of you. Notice that all three of the random variables have the same distribution, uniform. And here for the buying price, that's the runif command, where the first argument is 1, meaning you want a single random variable at this point. And then you need entries for these two positions. Right, that's a lower and an upper bound. And you can reuse that runif for both the repairs and the sell price. Give it a shot. All right, you've had some time to either figure it out yourself or start struggling with things and realize places where you don't know what to do. That's good. That means we can address how to figure that out. All right, so here, oh, that gave everything. I didn't want that yet. Oh, well, let's just go. That's what the slide gave. So, the first entry, right, the first blank you had is replicate. How many replicates do you make? Just a big number. That's all you need there. In this case, I gave 100,000. All right, the buying price is now the random uniform. We want only one of them. And we want that to be anywhere from 12 to 18,000. Okay? The repairs, likewise, are a random uniform. We want one random number, and we want it between 0 and 1,000. And same thing for our sell price, between 15 and 20,000. Okay? How do we calculate the profit? It's our expenses minus our revenue. Or other way around, revenue minus expenses. All right, in this case, the revenue is the buy price. I guess it expects me to have a laser pointer. It won't let me move the mouse over this. Buy price, that's our revenue. Or excuse me, the sell price is our revenue. And we subtract off our expenses, which are the repairs and the original purchase price of the car. What happens if we do this? Okay, that should all run in one step. It should run fairly quickly because this is kind of straightforward. Well, when you have a simulation, you can ask it for a summary. By the way, if this ever happens in our studio where it says do try catch, that's our studio yelling at you for not having a large enough plotting window. What's funny is we're not plotting anything. I wish I knew how to fix that, but that's what's going on. All right, we can ask for a 5-number summary. So the summary function in R, if you give it a vector, in this case cars is a vector of 100,000 different instances of this car business. Gives you a 5-number summary plus the mean. So our average, our expected return from this investment scheme is about $2,000. However, we see that we can swing anywhere from negative $3,000 or almost negative $4,000 up to $8,000. We can visualize this. We can just ask for a histogram of our cars. Okay. Notice that's almost bell-shaped. It's actually like a triangle, right? Looks more like a pyramid. That's because we're using all uniform distributions. Side comment that might help you on your homework and possibly on the exam. It's often tempting to not include all of the randomness and simply just put in the average. Well, you know, my repairs go anywhere from 0 to 1,000, so I'm just going to put in 500. What's tricky about this? You're going to get the same expected value, about 2,000. What happens though? Your variability condenses. So notice we don't go up to 8,000 now. We're about at 750 because we took off that extra $500 at swing room, right? And we don't go down to negative 4,000. We go down to negative 3,500 because we took out some of that extra swing room. So just be cautious if you discover yourself having the correct expected value but the wrong standard deviation or spread, that could be the culprit. Yes, sir?
So what they're looking for here is for our answers mean?
What was the question I asked? Oh, expected profit per car? Yeah, so you want
we use the
2,000.
mean?
Yes, we use the mean.
Okay.
Yeah, thank you for bringing me back home. So yeah, if you're looking at the expected profit, that would be the mean. So you can just type mean of cars. And what I was trying to point out as well is you can replace each of these three with the mean and still get the right answer, but you'll have the wrong variability. Right? Because if you ask for standard deviation, right now I've got 2,200 and change. If I redo it, whoop, that's the same number. It's a slightly smaller 2,200. But if you take one of the bigger numbers, you'll see this effect greater. So for example, if our buy price is restricted to 15,000, which is the center. All right, we still get about 2,000. Ah, there we go. Dramatic reduction in standard deviation, in variance, spread, etc. All right, but hopefully you don't fall for that, and every time there is a question of randomness, you include that as a random variable. So for our last question, that's what I say here. You can do histograms, means, standard deviations, because all you've got now is a vector of a random variable. Pretty complex random variable, because there was a whole process going on there. But you just summarize it as you would a random variable. Usually you're asked for the mean and standard deviation. All right. For our last example, we're going to flip back to the real estate from the decision tree. So you remember when we introduced simulation, both myself and your professor's slides said this is what we do when things become more complex than a decision tree can handle. So once again, you're an investor who buys and sells real estate. You're going to buy a house for $100K. You're going to remodel the interior for $20,000. You're going to sell it for $150,000. However, the foundation issues are no longer a simple $45,000 repair. As in the real world, it could have lots of issues or just a little bit. So our foundation repair is now a gamma distributed variable with shape 20 and rate 1 over 2,000. Okay, you haven't talked a whole lot about the gamma distribution in class. That's okay. All you have to know is, just like we say R norm for normal, And R unif for uniform, we just say R gamma for gamma. Okay? So what's our expected profit for investment? All right. As you can tell here, I'm going to have us write the code together. So we're going to replicate still. So let's just give it some nice large number and open these curly braces. All right, what do we need to know? What's random that's happening here? What's our profit if everything goes fine? Do you remember? So we earn 150. Let's subtract out our expenses. We get 30. All right, so let's just put our baseline profit is 30,000. Now this, well, let's make this complete. Is 150,000 minus 20,000. Let's start over and give you a no shortcut version so that this is better for studying. Okay, we're going to buy our house. $100,000, right? Okay, we're going to do $20,000 of repairs and upgrades. It's trying to autocomplete for me, which is really nice, but I don't want it to. All right, what happens if we're repairing things and we discover an issue? How often are we going to discover an issue? 20%. How do we simulate that in replication? Say it. Our norm, close. Our norm gives us a random number, right? We want a flipped decision. We want yes or no. In R, we're going to generate a random one of those with R binom. Okay? You haven't done this in your homework yet. Here you go. So to get a random event with R binom, this simulates a binomial variable, which is slightly confusing because you have both a number and a size. For now, just put 1, 1 for both, right? We want to flip one coin once. That's what that's saying. All right, what's the probability of heads for this coin flip, quote unquote? 0.2, right? Because this is if we have an issue or not. Right? If this comes up as a 1, we've got an issue. If it's a 0, we have no issues. Okay? All right, what happens if we have an issue? How much does it cost? Remember, this is an R gamma. We want one of them. All of your R functions, well, not R functions, all of the functions in R for generating randoms, the very first thing it wants is the number 1, which is the number of random ones you want from it. In this case, we want just 1 right now. Okay, this has a shape of, what did I say? 20. And a rate of 1 over 2,000, right? Okay. Then our sell price is 150K. Maybe we do all of our business in the same neighborhood. We know exactly what things should sell for all the time. So, what's our final profit on this house? Start with the simplest part. We bought the house, right? So minus the buy price. Okay? What happened next? Minus the repairs. Okay? What happened next? We discovered an issue or not. Right? Say it again? Exactly. Why do we do that?
And then there will be a coefficient for the issue cost, but if they don't, there isn't an issue, it'll replace it 0, and then that one.
Perfect. You can do this with if statements or if then else or if else, different constructs in R to handle these situations. But if you think about it just like that, it's actually, I think, a little simpler, right? So what you did here is you took issue, which is a 0, 1. It's 1 if you have an issue. So now you have 1 times the cost. So you're subtracting the issue cost. That's exactly what you want to happen if you want an issue. If you have no issues, that'll be 0, and you have 0 times your issue cost, which is 0. So it's taken out of the problem. Great. And then last, we just add in the sell price for our profit. Okay? That's it. Right? We're going to have the profit, and we're going to turn this out. We're going to get the expected profit in the end. So let's run the replicate. Oh, what happens if I run the replication right now? It's going to all spit out on my screen. There'll be 100,000 things I can't save. So let's save it from the get-go. And plot our histogram. What we see is we've got a lot of profitable houses, right? Each of these houses we're making 30 grand because there's no issues. If we have an issue, we start getting this wide distribution of possibilities based off our costs, right? That random variable only comes in if we have the issues, and that's what we see in our histogram. Well, what's our expected profit in this case? Still $21,000 and change. Okay. Any questions? What we've shown here is a way to combine a 0-1 variable with a cost to turn that cost on and off. And if you feel more comfortable doing that with an if-else statement, great. That's just fine. We are past our 3:30 time. I thank you all for coming out. If you have any last questions on simulation, we'll take them. We have the room until 4, and we can take your individual questions until then. Thank you very much.